2, 1, 0, and liftoff. The final liftoff of Atlantis on the shoulders of the space shuttle. America will continue the dream.
The size of the solid rocket boosters used on the space shuttle were determined by the width of the backside of 2 horses.
Measurements have a long and interesting story.
They have implications across the history of air and space, from the space shuttle to the Wright brothers' first airplane that you see behind us.
Yes, that's the real one.
They built kites and gliders to learn about flight before designing the first airplane.
They also used measurements and data to help them make decisions that led to that first flight.
Today, we are taking a journey to explore measurement and data and learn how accuracy has improved.
This is STEM in 30.
You heard us right. The size of the solid rocket boosters used on the space shuttle was determined by the size of 2 horses' backsides.
And while that might sound crazy, some of our measurements lead back to things that you might not even expect.
The measurement we know of as the foot is 12 inches long and is rumored to be that because it was the length of King Henry I's foot. But there is some debate about that.
Early on, an inch was considered to be the width of a man's thumb. Then in the 14th century, King Edward II of England decided that 3 grains of barley placed end to end would be considered 1 inch.
Long ago, a yard was considered the distance between your nose and your thumb when your arm is stretched out.
The origins of many measurements were not very accurate. And that leads us back to how the space shuttle relates back to 2 horses.
In the United States, the standard gauge of railroads, or the distance between the tracks, is 4 feet 8.5 inches. This gauge in the United States was carried over from England, where that measurement was used on tramways, which were smaller, localized railroads.
The measurements for tramways was based on the tools they used to build wagons. Wagons used the same measurement for the spacing between the wheels.
Many of the old long-distance roads had ruts from years and years of use by wagons. Any wagon that didn't match this size would break if they tried to travel the same road.
These old long-distance roads were built during the Roman occupation of England. These ruts were first made by the wheels of Roman war chariots, which were all made alike with a distance of 4 feet 8.5 inches between the wheels.
Roman war chariots were pulled by 2 horses, side by side. This seemingly random distance was used to accommodate the widest part of 2 horses, their backsides.
When engineers were designing the solid rocket boosters for the space shuttle, they had to account for transporting them from the factory in Utah to the launch site in Florida. This was done by railroad, so the size of these boosters was limited to what could be transported by train. And the size of those rails relate back to the size of 2 horses standing side by side.
The size of the solid rocket boosters used on the space shuttle was determined by the width of the backside of 2 horses. We'll be back to the Wright brothers in just a bit.
A bit? That's not a very accurate measurement.
It's a little less than a tad and a hair more than a skosh, but we're at the place where they do accurate measurements.
Today, we are at the National Institute of Standards and Technology.
The Constitution grants Congress the power to standardize weights and measures. Measurement is so important that George Washington mentioned it in his first inaugural address. The National Institute of Standards and Technology, or NIST, is one of the oldest physical science laboratories in the United States. NIST was established by Congress in 1901 to advance the way things were measured in the United States, which at the time lagged behind the United Kingdom, Germany, and other countries. Today, NIST measurements support the smallest of technologies to the largest and most complex of human-made creations, From amazingly small devices, so tiny that tens of thousands of them can fit on the end of a single human hair, up to earthquake-resistant skyscrapers and global communication networks. Our power grid, electronic health records, amazingly accurate clocks, nanomaterials, and computer chips all rely on technology, measurement, and standards provided by the National Institute of Standards and Technology.
We are joined by Vincent Lee, who is an engineer here at NIST. Thank you so much for having us in your lab.
Absolutely.
Why is measurement so important?
Well, measurement helps define the size of a part. Now, for example, when car manufacturers manufacture cars, all the parts come from all around the world. They're no longer centrally produced in one location anymore. For example, here I have a part. This part is made in the United States. However, this part is made in Japan. Yet, when I tell a manufacturer the specifications between the hole and the cylinder, they fit perfectly. And that's because we use a standard unit of measure, and around the world, it's called the meter. So now, if I take this bolt, which is made in China, and put it in here, it actually fastens it. This all fits together.
Why is accuracy so important when you're dealing with pieces from all over the world?
Accuracy is important because we want to make sure that the parts are made to a specific tolerance. Now, tolerance is the bounds or the limits of a part size. Now, if you take this metal boss here, and it was not measured accurately enough, it might be too big and won't fit in on this plate. Or this hole in this plate might be too big and you'll have a sloppy fit. And when you have a sloppy fit, inaccurate parts, you'll have poor performance.
What kind of measurement do you do in this lab?
So in this lab, we calibrate measuring tapes. A lot of tape manufacturing companies will send us a tape to ensure that it is manufactured correctly. We test them to make sure that they are manufactured to the accurate specification. We have a quality system, and in that quality system, we'll actually etch a NIST number on it so that it specifically identifies it and allows it to be traceable back to NIST and back to this facility.
So can you show us what all this does?
Yes, absolutely. So behind us is a bench used for calibrating measuring tapes. And when customers send us measuring tapes, they want to make sure that these tapes fall within a specified tolerance. For example, for a 30-meter tape, it's probably going to be within about a millimeter. In order to start that process, what we do is we clamp the tape down onto this bench, okay? And then we start by zeroing the laser at a mark. In addition to measuring the length, this length is only valid at a certain tension, and the tension is at about 5 kilograms.
So you have to pull it at a certain amount of tightness to make sure that it's accurate.
Exactly. So, and those are what we call validity conditions for the tape. It's a condition which that measurement is valid. In addition to that, this tape tunnel is controlled to 20 degrees Celsius or 68 degrees Fahrenheit within plus or minus a quarter degree Celsius. So, and that's to ensure that the tape is consistent throughout its length, because as you all know that metals tend to expand and contract with temperature.
So if we took this to the Arctic, we might get a little bit of a different measurement.
We'll get a slightly shorter length. Yes.
How do you measure this? Is it lasers?
So yes, we use a commercial off-the-shelf laser interferometer system to measure the length of the tape. Now, the way a laser interferometer works, it uses the waves of laser light to measure the movement of this carriage. It comes out in waves, and the wavelength, that is the distance between the peaks of the light wave, is a known and stable distance.
Can you show us how this works?
Absolutely. So first, I will align this microscope, and what I'm doing is I'm trying to align the crosshairs to the center of where the line of the tape intersects with the bottom edge of the tape. And once I've done that, I'll command the computer to measure this point and say, this is my 0 mark, and then I'll slowly walk it down. So depending on how many number of counts the waves passed, it counts the distance. And now we've come all the way to the 30-meter mark. I'll realign it to the mark of the tape again, level the carriage, and then take a measurement point.
Vincent, we've measured the tape measure. How accurate is this tape measure?
So this particular tape measure is accurate to within about 1 millimeter of the indicated mark. So now that's about a part in 30,000. That's a very good tape. Now, once we're done calibrating these tapes, we'll supply the customer with a calibration report, and that calibration report will state how accurate the tape is within the indicated mark, as well as a measurement uncertainty. And that measurement uncertainty for a 30-meter long tape is going to be about 0.2 millimeters.
So is that a plus or minus from what it's supposed to be?
That is exactly right. Well, Beth and Marty, thank you for coming here.
Thank you for showing us this. This has been great.
Well, awesome. Now, why don't you guys head over to the museum? They got something cool to show you over there.
We've moved to the NIST Museum, and we are joined by Sarah Reeves and Keith Martin. What are we looking at?
So what we're looking at was the US official standard for the meter bar.
Why is this important in the scheme of things?
So all length measures in the United States were measured against this bar. So if we took this bar and broke it in half, we'd all get twice as tall, because I've now changed the definition of length for the United States.
So how was this used?
So this is the master standard. So we would make copies for industry, and they would make working copies. So any ruler that you might own or any length measuring device, that's ultimately traceable back through a chain of measurements back to this 1 meter bar.
And do you still use this today?
Today we actually use more natural constants to actually make more precise measurements of it. The definition of the meter has never changed. For example, the length is still about 3 feet, 3 inches, thereabouts. However, the way in which we measure it has been able to get more and more precise. So we started out where we used the human body to make measurements. A foot was a foot, but it was very quickly realized that not everyone's foot is the same length. So then we went to bars like this as an abstract of how to measure the length of meter. And now, as I said, we're back to using the natural state.
So when I measure a meter, I will often step it off. Let's see. I just happen to have a pair of shoes with me. Is this going to be, if I measure this with 3 shoes, we're not quite there. That's not a very accurate measurement, is it?
No.
Why is accuracy so important?
The better you can measure something, the better, in our case, the better science you can do, or the more accurate a measurement will be.
So why is it this shape, and what is it made out of?
So the bar is actually an X shape, and I'll pick it up for you here. The shape is actually designed so that it is more balanced for doing the measurements, and it is made out of platinum and iridium, which the 2 metals combined actually won't contract or expand, so you won't be changing your measurement as you use the bar.
Because thermal expansion could cause a real problem on this, couldn't it?
Yeah, definitely.
Why is it important that we measure something the same way every single time?
Well, if you want to produce a working machine, like say you have 2 clogs, you want them to interact properly, right? And if they're different shapes, they wouldn't work. So think about all the moving parts in a car. They all have to work together precisely, so they need to be measured accurately and the same every time.
Awesome. Well, thank you so much for showing us around today.
Thank you for coming.
Thank you.
Appreciate it.
Measurement plays a huge role in aviation, everything from wind speed to fuel weight.
Let's learn a little bit more about how measurement affects aviation.
I'm Dr. Bob Vanderlinden, the Curator of Air Transportation at the Smithsonian's National Air and Space Museum. Behind me is an Air France Concorde, one of the first aircraft to fly supersonically and carry passengers across the ocean. The Concorde could cruise at Mach 2. Generally speaking, Mach 2 is about 1,300 miles an hour. A conventional airliner is a transonic airplane. They do about 0.8 to 0.85 Mach, which is, depending on the airplane, between 500 and 600 miles per hour. Measurements, weights, mathematics, extremely important for aircraft design and for flying the airplane. Pilots have to know what the airplane can do, its cruise speed, the altitude it flies, its range. A lot depends on the weather. Is it hot and high for takeoff? It requires much longer runways because the air is thinner. All of this has to be calculated. The weight and balance of the airplane is extraordinarily important because the whole purpose of the airplane is to carry you and cargo. But if it's loaded improperly, the airplane won't get off the ground, at least not safely. It's a wonderful airplane. I gotta tell you, it's probably the most beautiful airplane ever made. It's just gorgeous. And it's all designed to a purpose. It's not designed to be beautiful. It's the physics and how the engineers solved it. You know, the beautiful wing, it curves that way for a reason. You know, the nose is that pointed, that's for a reason. Every design, every element is there for a reason. Aircraft are built to extremely close tolerances. For obvious reasons, they need to be extremely strong. Everything needs to work very well together and stay together for decades. It's built like a fine watch. In the case of the Concorde, that was even more important because as an airplane, especially a supersonic airplane goes faster, heat builds up, and the airplane actually expands. In fact, the fuselage on the airplane would stretch about 8 to 10 inches. The calculations to figure out exactly how far it's going to expand and contract, got to know what the temperature is going to do. You got how hot that's going to be. You have to know how the material, and in this case, aluminum alloy, is going to react, how it's going to expand and contract, what will it do to that alloy over time. All sorts of factors are involved with it. Accurate measurement is important in the design of all aircraft, but it's even more so for the likes of a Concorde, which can fly at twice the speed of sound. And it's just a gorgeous airplane. Yeah.
It takes a lot of thought, measurement, and design to get modern aircraft off the ground. But what did the Wright brothers have to consider when trying to get their first airplane flying? One of the hurdles the Wright brothers had to overcome to invent the airplane was the ability to control it aerodynamically. One of the major stumbling blocks was how to control the roll of a flying machine, which allows the pilot to steer an airplane. Other inventors built gliders and controlled the roll of the craft by shifting their weight, which worked but wasn't practical. When observing large birds in flight, the brothers noticed that they would change the shape of their wings to achieve roll. But how could they do that with an airplane wing? The idea came to Wilbur while playing with an inner tube box. He noted that if he bent the box in a particular way, one side of the box went up while the other went down. He thought that if he could make a wing bend like this, he could achieve roll. In order to test this theory, Wilbur built a model of a bendable wing in the form of a box-shaped kite. The kite was controlled by 4 lines attached to the front corners of the wings. The lines were then attached to 2 sticks, and when Wilbur angled the sticks in opposite directions, it caused the wings to twist, causing one set of the wingtips to turn upwards and the other downwards. By controlling the wings of the kite in this way, Wilbur caused it to roll, suggesting that a full-size aircraft could obtain roll in the same manner by bending the wings. The brothers referred to this as wing warping and continued to test their control surfaces on larger models, or gliders. Some were more successful than others.
We've moved to AeroLab. Here they design and build wind tunnels used by organizations all over the world, including museums.
Very early on, when the Wright brothers first started to seriously study the problem of human flight, Wilbur wrote to the Smithsonian searching for information. The information and publications they received was the most widely accepted scientific data at the time, but it didn't match up to the experiments they had been conducting.
The Wright brothers realized they needed to collect their own data. To do this, the brothers developed their own wind tunnel. The new data collected from their wind tunnel testing opened the way to the development of the first airplane capable of sustained, powered, and controlled flight.
Let's go look at some wind tunnels.
Hi, Marty and Beth. Welcome to AeroLab.
This is Hareen Aparaka Kankanangay. He is the CEO of AeroLab. Hareen, thanks for having us today.
Oh, it's my pleasure.
We have a couple of questions, but I'm going to start with an easy one for you.
Sure.
What is a wind tunnel?
A wind tunnel is a tool that aerospace engineers use to study the aerodynamics of airplanes, cars, buildings, drones, just about anything that experiences airflow.
Tell us, what does AeroLab do?
So here we design and manufacture wind tunnels, and that's all we do. And we also service wind tunnels, and then we also do installations of wind tunnels as well.
And who all do you make wind tunnels for?
We make wind tunnels for universities, governments all over the world, and then commercial customers all around the world.
And I understand you're making one for us?
Yes. So we are building you guys a new walk-in wind tunnel. It's where you can walk into the tunnel and experience wind, and then you can put on these wings and go in there and try to experience what lift is like. And then we also have some other wind tunnels that AeroLab has had at the Smithsonian since the 90s, and at the old How Things Fly exhibit. And so all that's going to be refurbished. So all that's going to get, it's going to go back to the Smithsonian as well.
Who needs wind tunnels?
Wind tunnels are used by universities. It's used by the military. Those are mainly the main customers, but basically researchers and educators.
Why do you need to build wind tunnels? Can't you just run these simulations on computers?
That's a great question. In the 90s, at one point in time when computational fluid dynamics was really ramping up, and engineers and scientists were using it, they thought that wind tunnels were going to go basically obsolete. And so you're not going to need it anymore, because these computer simulations are going to just give us the answers that we need. But really what engineers found was that the simulations weren't enough. The computer technology was way far behind to basically accurately simulate what a wind tunnel can do. So the way I see it is wind tunnels won't ever go away. Instead, all these new things like computational fluid dynamics and AI, it's just going to be tools that's going to be in the toolbox that's going to help engineers develop products better and help come up with better research.
When you talk about fluids, most of us think about running water, but that's not all fluid dynamics is about.
No, so you have air, you have water, you have different liquids like oils, and sometimes aerodynamics is actually used to look at the blood flowing through your veins.
And is it cool to see the research that comes out of these wind tunnels too?
All the time. We built a wind tunnel for a professor in Princeton. She's using this wind tunnel not to build airplanes, but she's essentially studying morphing wings. And so kind of like what an albatross bird does, right? It's, flies around the world and doesn't use all this energy, but it can move, it can change the shape of its wings essentially to be very efficient and use as less energy as possible. So she's actually looking at that, and she's trying to incorporate some of these things into like everyday wings.
Can we go look at some of your wind tunnels?
Sure, follow me.
Oh yeah, okay.
There it is. That's cool.
We call this our mule. And so it's basically an educational wind tunnel. And what we do with this is that we use this to test out new software that our engineers come up with, any sort of electronics, probes that we want to test out, and some of the motion control stuff. These are some of the things that change fairly often. So the way this works is we enable the tunnel. I put the set point to, let's just say 50 miles an hour, and you start the system. And here you're reading the airspeed over here. If you want to go to, say, 100 miles an hour.
I can hear the fan speed up.
Yep.
That's cool. That's cool.
That is cool.
Nice.
Yeah. Maureen, thank you so much for showing us around today.
It's been my pleasure.
Here's a look at some other wind tunnels. The first use of wind tunnels was 30 years before the Wright brothers' first flight, and since then, they have continued to be used in aviation. Advances in computer technology have allowed for computational fluid dynamics, or the study of how air moves using computers rather than actual models. These computer models are important, but wind tunnels and testing scale models still play a vital role in the development of next-generation flying machines. Using wind tunnels allows engineers to test the findings of their computer models. There are several types of wind tunnels, including those that test speed, configuration, style, and output. Designs are improved using wind tunnels by finding areas where aerodynamics can be improved. Improved lift-to-drag ratios leads to better flight times and resistance to turbulence. Some wind tunnels can also be used to simulate turbulence, to study different flight situations. Wind tunnels are not only used for aircraft. Vehicles like the car you ride in and race cars are tested in wind tunnels. And even tall building models are tested in wind tunnels to see how they will hold up to sustained winds at high levels. Engineers today use every tool at their disposal to improve safety and performance. As we've learned today, measurement and accuracy are incredibly important, especially when you're flying.
Now imagine how important that becomes when you're sending a mission to another planet.
We got a chance to catch up with space history curator Matt Schindel to learn about a Mars metric mistake.
I'm Dr. Matt Schindel. I'm a curator here at the National Air and Space Museum, where I curate our collections related to Earth and planetary science. So after the end of the first era of robotic exploration of Mars ended in the 1970s, it took about 20 years before the US started sending spacecraft to Mars again. And so in the 1990s, you started to see US missions to Mars again. And there were a couple of missions sent during that time that unfortunately had poor ends. And one Mars spacecraft that had a particularly bad end was the Mars Climate Orbiter, which the US launched in 1998 on the way to Mars. And when it got to Mars and when everyone was ready to celebrate the fact that it was going into orbit, suddenly NASA lost communications with it. And what turned out had happened was that the software on the spacecraft had a different software from the software that was being used at Mission Control, one of which used metric units and the other used English units, or feet and inches. And those two software were supposed to be able to communicate with each other, but because the numbers from one weren't being converted into the units of the other, the spacecraft either ended up burning up in the Martian atmosphere or speeding off, out of orbit of Mars and ending up in an orbit around the sun. We don't actually know what happened to it, but we know that we didn't get the years of data that scientists were hoping to get from the Mars Climate Orbiter because we lost it. So this is why when we write down our measurements, it's important to actually indicate what units we're using. Otherwise, you could be communicating something very different from what you think.
Well, we're back to where we started.
It's amazing how these two and their machine changed the world.
It didn't just fall together. It took accurate measurements, models, and trial and error before it first took to the skies on December 17th, 1903.
The next time you measure something, think about how accurate you're being and how accurate you need to be. That was STEM in 30.